Our journey starts in the Oort cloud, which is speculated to exist just beyond the Sun's gravitational pull. The Oort cloud is estimated to cover up to 15 trillion miles and consist of billions of bits of debris. These range from the size of dust to objects which are hundreds of kilometres across. These particles forge together along with ice, gas and dust to form what we know as comets, but can also be referred to as a dirty snowball. This is only a fraction of how big this Oort cloud really is, if it were to exist. It's commonly thought of to be the garden gate that leads us to all other neighbours throughout our galaxy. The gas planets, Jupiter, Saturn, Uranus and Neptune, are said to have a strong gravitational pull and could be a reason why comets come from afar and enter our solar system. But in other cases that we see here, our comet collides with another and now its journey begins. The comet will go to wherever there is a gravitational pull. In this case, it happens to be our solar system. After travelling at an average of 50 kilometres per second, our comet will take roughly 2,800 years to reach Pluto's orbit from the Oort cloud. Pluto is the furthest planet from the Sun, primarily composed of rock and ice. It's also the coldest, bearing temperatures of -233 degrees. However, it has been orbiting our solar system ever since it was first created. Could signs of life perhaps be preserved in this icy world? Our comet proceeds on throughout its journey of our solar system, and after 20 astronomical units it passes Saturn. Saturn is an incredible gas planet and is primarily composed of hydrogen with small proportions of helium. The rings extend to over 100,000 kilometres with an average of approximately 20 metres in thickness and are composed of 93% water ice. They range in size from specks of dust to the sizes of small cars. The next phase of our comet's journey takes it past Mars. Mars is the closest planet to ours in its similarities. Mars has surface features reminiscent both of the volcanoes, valleys, deserts and polar ice caps of Earth. It holds the highest mountain in our solar system and is home to the largest canyon. As we approach the end of our comet's life, we notice that inside the comet there is something called a nucleus. The nucleus is the core of the comet, which contains bits of rock and dust bound together by frozen water and other types of ice. These substances may have provided the raw material for planets, as well as the chemical building blocks for life. Depending on the comet's trajectory, it is roughly around the orbit of Earth and Venus that the comet starts heating up. It is only at this point when we can get a clear view of our comet. Prior to this time, most comets are almost invisible and next to impossible to spot. As the nucleus of the comet starts to heat up, a reaction called sublimation will begin to occur. This is a transformation from a frozen solid directly into a gas. As space is a vacuum, a liquid cannot exist due to a lack of pressure, causing it to convert directly into a vapour. This causes a dense atmosphere of water, carbon dioxide and other neutral gases as well as dust grains. This cloud of gases is called the coma. It surrounds the atmosphere of the comet and can extend for millions of miles. The cloud is very thin, however, 10,000 times thinner than a cloud in the Earth's atmosphere. As we now pan out away from the comet, you can see two towers, one that is blue and the other that is white. The blue tower is composed of plasma. The tower is formed because the neutral gas initially presented in the coma is ionised by solar radiation, giving birth to positively charged ions. These ions are susceptible to magnetic solar forces and are repulsed by the Sun's own positively charged solar winds. They are therefore swept out of the coma into a long characteristic ion tail, which can reach a distance of an astronomical unit. This is equivalent to 96 million miles, which is one Earth's distance to the Sun. The white tower is composed of dust grains that form from the rush of sublimating gas. The tower appears white due to the particles reflecting light from the Sun. The most common particles have diameters of about 1,000th of a millimetre, but due to the staggering amount of these particles, these form the most visible part of the tower. However, these particles can have diameters of up to many tens of centimetres, which can be ejected by the gas flow from a very active near-Sun comet. The white tower is pushed away by the radiation pressure in the comet. This tower then follows the comet's orbital path, since even the smallest thing has a density that is controlled by the Sun. Comets lose ice and dust each time they return to the inner solar system, leaving behind trails of debris. When Earth passes through one of these trails, the debris burns up in our atmosphere, effectively becoming meteors. This provides us with a phenomenal display we know as meteor showers. As we near the end of our comet's tremendous and long journey, you can see in the overview that the comet is relatively small, especially when viewed in the depths of space. The end of a comet's journey can be caused in a number of ways. Some can be due to a collision with a planet or a larger interplanetary object. Others may be propelled further into space, never to be seen by us again. Some comets, such as Halley's, can even be caught in a highly elliptical orbit around the Sun. But others, such as our comet, are drawn into the Sun's tremendous gravitational pull and incinerated. This concludes the end of our journey through our solar system as viewed through the eyes of a comet.